Let's talk. Where are we? What have we been doing? What are we wondering about? We've looked up. I hope you've gone outside to see things. And there's our mascot there. She's been looking up for a long time. Right. 1,000,000,000 seconds is about 1,000,000,000 heartbeats, or 32 years. And she's been wondering, mapping things out, and she's been wondering about things and wondering, like, well, it looks like everything's going around us. But I wonder, is that true? Are things going around? It doesn't feel like Earth is moving, but well known, it doesn't take much to realize Earth is not flat. So that idea, does things just around us? Or are we moving around sun? Why would someone move? Why would someone think that? And why are those things over there? Why am I afraid that you'll see those? Oh no. What? Why? Don't look. Don't burn me at the stake. Witchcraft. We don't have these yet, do we? So, what's up? How do we figure this out? Well, one way to figure it out is to, read chapter 3 and 4 in the book. And in the book, we've got these ideas. And so we're going to lay out a very incomplete history. I'll give you an idea. Okay? So let's give you an idea here. Chapter 3. Okay, so we're going to take ourselves from antiquity, 2,000 years ago plus, more than 2,000 years ago. Think about it around then. And we're going to take ourselves from observing things, so I got some clues, and wondering about things. Well, what do you think? Well, I think this, but do you know? How do you know? 3 dudes of ancient astronomy. I'll just mention they bring up really good ideas, really good examples of some considerations. Then we go to a way of knowing, certainty and science, and a profound idea that I think should be taught to all kids, and it actually engages them. They like this when you do this, and it's a very profound idea, unless you're trying to teach people to just believe you and not talk, let me say nicely. So we've got these from watching. Chapter 1, Chapter 2. What's up? Oh, I've measured things. I've observed things. What's going on? We want to know. We got some stories. We got some guesses even. We'd like to know. 2 to a tie. Ptolemy versus Copernicus. Now this is kind of fun. So I don't expect exact dates, and it's an incomplete history. It's not a history class or an anthropology class. But Ptolemy, and you see this in the book, was about 150, and the CE is Common Era, sometimes called AD, but that's really assumes that everybody's Christian, and they're not. So Copernicus, just add a 0, and you're in the ballpark, easy to remember, Common Era. Okay. When I talk about dudes of ancient astronomy, we're going to talk about before Common Era, often called BC, so it's kind of easy to remember. But before Common Era, this is common notation. So we're going to talk about these two, and that long, more than 1,000 years, still a tie. Crazy. What do I mean by a tie? I'll show you, and you see it in the book. So we get it both ways. Heliocentric alignment. So we're going to start piecing together some ideas and some terms, because we've got a job to do, a challenge to meet in chapter 4. Angles. Now this section you can skip or skim or do, but do. Don't skip or skim this. Do exercise number 9. It's important. It's on parallax, and that's important. It'll show you why things appear to be moving slowly in a distance, And then if you want a distance in light years away, you can't even see them move. So that's there. I'll just say this now, and I'll say it again, that if you find yourself interested, so this is a descriptive astronomy class, it's something for everybody to look up and wonder and connect as humans to this endeavor, this journey. This is a journey, it's a human journey, right? And so we're looking at that. I'll talk about that in a second. But if you find yourself taken, like, I want to maybe do astronomy. Well, astronomy involves a lot of math and physics, right? You use computer programming and electronics, and people do different things. So the details require this kind of math. So if you're interested in that, you might play around with that. All that I want you to focus on here. I went a little bit far just to give a taste for those that want it. So hopefully that's a relief. You don't have to be able to measure and calculate how tall the tree is across the river. Tycho or Tycho Brahe and Kepler. We'll talk about Kepler's laws. There's going to be K1, K2, K3. Now, when are we talking here? By the time we're getting here, we got Copernicus, and then we're going to lead over to here. And we'll talk about how they're connected. And Galileo at the same time. So I'm going to call these 1, 2, 3 around 1600. Renaissance and late Renaissance in this era right here. Idea of connecting us as humans, art, science, wondering, not just believing or being told what to believe, but challenging that. You can see where that goes back to and how dangerous it got here. And then over here in England, Sir Isaac Newton pulling all this together, 3 laws of motion for all objects, not light, but for all things made of matter, and universal gravitation and the scientific revolution. That's quite a journey. It was slow going initially until we got these certain ideas and methods. And we're going to talk about that. And with that, we have technology all around us. I'll save moon missions and global awareness till chapter 6. But this is a human journey, right? We all started as some thousands of people, just thousands. Now over 7 billion people on the globe. And, you know, we started in Africa, right? We know this. We can measure these things. We can see this. We can use geology. We can use anthropology, and we can tie things together. And we can piece together the story, dig it up, and see that we fanned out around the globe. And as we did, the globe itself moved over periods of time. So it's a human journey. We really are connected as cousins. And we really are scientists. Maybe we're not trained as scientists, but we do wonder about things. We're artists. We are affected by music and sound. I know you heard me say it before. Politicians, we got to make agreements. We got to figure out our relationship with ourselves and with others. Psychologists, what did I leave out? Athletes, of course, we have bodies. We're athletes. We can see people like, wow, you can jump that high. I'm jealous, but that's so cool that the human body can do that. But that cheetah is going to catch you if you better watch out. So anyway, this is a human journey. So let's take the journey. I know, it's incomplete, right? It's totally incomplete. But we're going to do it. So let's pop into the first section, these set of ideas. Again, we're going like over 2,000 years ago to about 300 years ago and the scientific revolution. The telescope didn't come onto the scene until just right near at the end there. So it played an important role. I'm sorry, in those 9 dudes there aren't women, and it's very limited. And so if you read the text, you'll see that, in fact, there were plenty of other people. It's just the text has already got enough. And so chapter 3, you can do that when we talk about others. So really we're getting some ideas. And what are those ideas? Well, we're going to talk about 5 clues, 3 puzzles, and 3 dudes of ancient astronomy. So let's do this. Okay, I think I've got that. So talking about it really quickly. This is just what we saw, right? This is what we saw as ancient shepherds. So these are our clues. Everybody would agree. Now you might make up different stories than me, but everybody would agree that star dots are fixed. They keep their same address, their same declination and right ascension on my map. They keep, so I can move this, but they keep the same place. Just like Earth is moving, it doesn't feel like it, and they didn't know that necessarily. Some wondered about it. But you keep your same latitude and longitude. So too, these stars keep their same place relative to each other. They move, but you can always find this star next to that star, etc. Okay, so they're fixed, but they move together. Planet dots, they just look like dots. They didn't think of them as worlds. So you got to think of them. They just saw them as glowing dots. What are they? Fireflies? Close? Far? What are they? Moon and sun, they wander. They change the declination and right ascension. They change the stars in which they're in front of, right? And so if I look over here, let me make sure you can see that, and we're rolling and all is good. Life is good. Okay, cool. Let's go over here a little bit. Get that glare out of there. Good. Okay. So, you watch. Of course, during the day, the sunlight comes through, and sunlight is a rainbow of colors as well as non-visible light. But the blue hits our atmosphere because of the frequency of blue and the type of atoms in our atmosphere. Don't worry about that. Blue light goes all over the place and makes our sky glow blue, right? So we can't see things when sun is out. But still, stars are way, way out there. As we know, planets and sun, AUs away. Stars light years away. These are the close ones in our galaxy. Okay, so that's cheating. Don't burn me at the stake. So here it comes through. They move together. They rise somewhere over in the east, and they go like this. I'm looking south because I want to watch the planets. You can watch north too. Right? Fixed. We know that. Everybody knows that. Everybody draws those dots, but you can connect them and make up your own story. Everybody knows that. Planets, sun and moon wander. Planets, moon, and sun are only seen in 13 zodiac regions. Sun moves along the ecliptic through that. Let's summarize that really quickly. You've seen this 30 million times. Let's do it. You'll never find sun, moon, and planets down here. You see them in this little strip here. Something like this, right? Without worrying too much. They're always in front of those stars. Why those stars? What's so special about those stars? That's where you see them. And so you look for your Black Panther. Okay. And who knows? Moon may be, let's see if I go sun over there, moon. Maybe moon's over here. And connect those dots, got that mastered. Shade this side. So light's coming from this way. So sun's got to be over here. Maybe it's sunset, What day would that be? Sun's there, right? And then on this day, they rise and everything moves together. If you look really closely, you might, and it depends on moon phase and time and stuff, but if you watch moon over the course of the night, you might see it shift by about maybe half a thumb, maybe half a fist, depending on how much just some, right? You might see it shift from when you see it earliest to when you see it latest, but it's a little difficult. So things are going to move together. The sun's going to go like that, it'll set, you start being able to see things, and there could be dots. In fact, last night it was really cool. Jupiter was right above, in fact, so moon was down here, Jupiter was like that, Saturn was over there. It was so cool, but you know what? I know that that's wrong. That bothers me. Why? Because those dots are outside of the strip. They're never outside of the strip. So I'm going to put some over here. I'm putting over here. Right? Whatever. And people go, ooh, look, the planets are lined up. I mean, sorry, I didn't mean it. I'm not making fun. But they line up. That was one of the clues. They're always here, and sometimes they're here, and you You just track it, and people did for a long time. So it all moves together in one night, rise and set. You will be very hard pressed to see any movement of those planet dots. They're not going to move much in a night. I don't think visually you're going to pick that up. Even in a week, it's like, drawing your little dots. But in a month, you really see some difference in the position. That is, what stars the planet is in front of, what stars moon is in front of. Of course, it's hard to see what stars sun is in front of, but we can figure that out. In fact, sun moves along that ecliptic. So where's that ecliptic? Where's sun's? Well, the next night is just about 1 degree, not about, you can calculate it, but over here, and 1 degree. And then, so sun, day after day after day, 1 degree shift, 1 degree shift, 1 degree shift, eastward. 1 degree shift along the ecliptic. Remember, there's no explanation for why yet. You're just observing. You're wondering why. That's the point. You don't have to understand. This is what you see. Why do you see it? I don't know. I just see it. Don't ask me why I see it. I just see it. But chapter 3 is about why we see it. So what other clues? Nightly, week to week, and monthly, they usually shift. So the next night, moon will be over here next. It's moved into near these stars, about a fist and half a thumb at arm's length, something like that, right? Whatever. Sun will shift just a little bit, about 1 degree, but again, hard to see. Can be figured out. It's hard. Planets can shift very, very little, but they all shift this way. Now remember, so this is tricky. The sky rises and sets that way, but the next night they will have shifted. The stars will be together, they're fixed. But these folks, they will shift. These gods, these whatever they are, right? They will shift, and you're going, why? And then, occasionally, if you watch month to month to month to month, right? You got this little business going, like, a couple months there, a couple months there, and that goes back here. And they go, what is that retrograde? Must be bad luck. People even today, Mercury's in retrograde. Yeah, Mercury's always in retrograde, or frequently in retrograde. You cannot tie that. There's always something bad, and you can always blame someone, but why is everybody picking on Mercury? Okay, 5 clues, 3 puzzles. So then you go, why? Why do those 7 wanderers, called the 7 planets, Sun, Sunday, Moon, Monday, Lunes, Martes, Mars, Miércoles, Mercury, right? Or mercoledì in Italian, Mercury, right? It's all connected, right? Where was I? I made it to Wednesday, didn't I? Yeah. Okay. Jueves, Jupiter, right? Viernes, Venus, and Sábado, or Saturn Day. Saturn Day. It's not Saturday. It's Saturn Day, right? So those 7 wanderers. Sun and moon never go in retrograde, but these little dots do. Why can't I ever see them here? Why don't they just go somewhere else? Aren't they bored? What's going on when the planet, not sun and moon, do the retrograde dance? And what's happening really? I mean, it looks like everything's going around us. It doesn't feel like we're moving. To the visual eye, I get why you might say it's a flat earth. But you don't have to travel very far and notice things. You got to notice, you got to pay attention. But I mentioned that it's clearly curved for many reasons, which I gave you in the previous. So there's the key. What do I mean by geocentric and heliocentric? Well, by geocentric, I mean everything goes around us. And they even thought that there was like a sphere of stars, of dots. What are they? Just going around us. And they go from the east and they set in the west, rise in the east and set. And everything seemed to do that. Seems like it. Doesn't seem like we're moving. Doesn't seem like we're flat, but it doesn't seem like we're moving. But when you look at these puzzle pieces, and you use some geometry, and look, they built pyramids, right? Stonehenge was clever, not quite as, but cathedrals, etc. But people were using geometry and mathematics. So some people were looking closely. Some people were looking beyond the stories and making measurements. Right? And they did some really cool things. But compared to us, it's basic knowledge, but it is impressive what they were able to measure and figure out. Quite impressive, and I'm not going to get into the weeds with that. 5 clues, 3 puzzles that led to the scientific revolution, that changed our lives, that helped save lives in the hospitals, right? That gave us electric guitars or whatever, right? So the question is, are things going around Earth, or are we actually moving around Helios? Are things going around Earth? We know what we see, but is it like it feels? We're not moving and things go around us? Or are we actually moving and going around sun? Now you may know the answer, because you may be an alien. Maybe you've gotten off Earth, or maybe you've watched National Geographic and all those other things. So these puzzles really were important to people, and people wondered. And so by pushing that and by saying, well, I don't want to guess, I want to know. How do I know? We developed this process, scientific process. Now, a lot of people had been thinking about this, and as I say, they were more impressive than I'm going to make them seem. Excuse my camera person there. Okay, so real quick, it's in the book, right? Listed here, so I'm just going to make this a quick thing. The Dues of Ancient Astronomy, oops. That's an A. I think I erased, I don't know what I did. Dudes of Ancient Astronomy, that's it. Why do I do that? Because that's their names, D-A-A, Democritus, Aristarchus, Aristotle. Now, Aristarchus, I don't know, whatever you got to do, Aristotle, Aristarchus, you probably heard of Aristotle, probably haven't heard of Aristarchus. And he did much more. I'm not going into all the stuff. So it was quite impressive what people did, right, in Baghdad and the whole Middle East and obviously Egyptians, and it's just impressive. Okay, fine. To get a taste, though, there's just an important idea here that really informs our government system and our Constitution. We're talking over 2,000 years ago, around 2,300 years ago or something like that, right? So before Common Era. He had this simple notion that you and I and things and trees and squirrels and rocks and air and water are made up of these indivisible little building blocks. And indivisible in Greek was atom, basically. He didn't have the notion of it the way we do today. In fact, we really, again, like so many things, it wasn't until about 1900 that we really understood that from this whole evolution of thinking. And that changed the game. Right? But he was right. So, yes. But again, he didn't know the details. So, and it wasn't without experimenting. He observed things, right? And this other person, Aristarchus, among the things he did, many things, heliocentric. He's the first on our list. I'm not going to say no one else thought of it, but he's the first on our list to say, you know what, planets, and Earth is a planet. This thing we're standing on is not one of those flat just things. We're actually a planet like that dot. We're like that dot. That's a crazy idea. But he said, you want to solve those puzzles? Look at those clues. And the good way to solve those puzzles with those clues is to have Earth going around the sun with the other planets. And then you will see that. You will see what we see. So he's saying Earth is like the planets. That's nuts. But back in the day, it was okay to say that. Okay? They orbit Sun, Helios, Ra, Inti, Sonam, etc. That's a hard sell, though, because it really doesn't feel like we're moving. Aristotle. You may have heard of Aristotle. Huge contributions, huge figure in science. I mean, if you had a small list of human thinking, Aristotle would probably be on it. And so he was often used as the authority. He was taught in universities for a long time. Like, oh, and it becomes dogma, like, I can't challenge that. Well, that, you can't say he's wrong, he's the authority. Don't challenge the authority. Well, science isn't like that. People might be like that. No, you can't go against the club rules. Well, fine. But if you want to know, you got to challenge great minds. Because he thought that things were made, he thought dry erase pens were made of some part, you mix up some air, some earth, some water, and fire, boom, you get a dry erase pen. Crazy. He thought that everything goes around Earth, geo for Earth, center, Earth at the center. He thought everything went around Earth. In fact, spheres upon spheres, and he said, out there's the heavens and everything's perfect and perfect shape and perfect spheres and unchanging. And others said this too, it's kind of building on this notion of the perfect heavens out there. Okay? Again, he was brilliant, but even, and then he talked about motion, he got that wrong too. I mean, he had some ideas. He wasn't, total props, but it doesn't mean you can't get something wrong. Einstein got some things wrong too, right? So that's fine. But the point here is if we want to have a healthy society, if we want to advance our knowledge, we need to be able to challenge the authority. We need to be able to challenge the President of the United States, right? Absolutely. We need to even not say nice things. We should be able to do it. It's better to be respectful of certain things, but there are some things that require loud voices, right? So that's built into our system. That's built into our Constitution. In fact, this notion that you challenge the authority took a while, and that's part of the journey that we're taking in chapter 3 to get up to this way of thinking. So that's the idea. How do you solve the puzzle? Not by authority, by looking. You get some ideas? Well, if you haven't got enough evidence, you're not going to convince everybody, even though you might be right. Got to go get the evidence to support it. And these puzzles drove people, right? And so we're going to look at that journey. Let's talk about certainty. And